So, as promised, we will start in time. I still see some customers coming in, but in the worst case, they will miss my introduction. So, let's start. Good morning, everybody, to the second session of our Digital Rutronik Forum. My name is Markus Balke. I'm acting as a Senior Marketing Manager for Analog and Sensors at Rutronik, and I'm your host today. The upcoming session will be presented by Tobias Bukowski from Infineon regarding predictive maintenance solutions. Infineon is well known as the powerhouse, but meanwhile, Infineon also has an industry-leading sensor portfolio, especially in the range of magnetic sensors. Today, you will see a live demo of the predictive maintenance solutions from Infineon, combining their strengths in sensors, microcontrollers, and security ICs. Ready-to-use solutions. This is also Rutronik's approach to help customers in reduced time to market, so that there is a perfect fit between Infineon and Rutronik at this stage. During the sessions, all participants are muted to avoid background noise, but please feel free to ask your questions via the question and answer function in WebEx. You can find this function by clicking on the three dots in the bottom menu line. And when you are asked to address whom, so please select host and presenter as the addressee, so that everybody from the organization team is aware about your question. We either will reply then by answering directly to the question in written or verbally after the presentation itself. That's enough from my side for the initial words. Now please enjoy the session. Tobias, the stage is yours.
Yeah, thank you, Markus. Thanks all for the warm welcome and for the nice introduction. It's a pleasure for me to present today Infineon solution, sensor solution here at Rutronik's Digital Forum. Just a short intro. I'm now switching on my video, and I hope you can see myself now. So is everyone able to see me? So Markus, just give me a hint. I'm wearing my mask.
We can see you, yeah. At least very small because you're on the presentation mode. So, but we can see you. Yes.
You can see me, which is good. So I'm taking it off now, which is in Corona times I wanted to stick to the formal process, but since I'm alone here in one of the silent boxes of Infineon, I can take it off now. So warm welcome from my side. The reason why I'm switching on my video camera today is also the reason, since we are not on an exhibition, we are not at Sensor and Test and an analog sensor and test. We are here. We have to do it digital this time. And this requires some more, I would say, pragmatic and hands-on ways to show and demonstrate the things that you usually exhibit on events or other fairs. So this time, please apologize for any disturbances, for maybe a bad quality. I try my best, and I hope that the sound and the video is clear enough to see at least the main things. I will start a demo, go over it with my video camera, and then I will have done some in the end some cuts of a video which are in the end pictures, and I will go through that PowerPoint presentation together with you. So first of all, my name is Tobias Bukowski. I'm Global Distribution Marketing Manager for Sensors. And let's start with the predictive maintenance demo that we prepared originally for the booth of Rutronik this year. Let me switch on the demo, and then I'm turning my video camera around so that you can see it. So it's getting a little bit louder, a little bit more noisy. I need to stand up. I hope that every one of you is able to see it. So what you actually can see here is, I hope that you can see it, is first of all, you might wonder what the cycling brake is for. I will explain that later on. Second
Tobias, I need to interrupt you. So we can see the presentation, so the PowerPoint in full screen mode, and you only very small picture.
Okay, let me enlarge that. Just a second. Just a second, I tried it again.
So maybe you should finish the PowerPoint at least for a second so that we can see you on a full screen.
Yep. check that.
Should be good enough if you finish. Yeah, now that's perfect. Now we can see you.
You can see me now?
Yes.
Okay, so big and clear. So I'm changing it, and I start the presentation again. So I need to stand up. So I hope that you can see it here. So I can't see myself at the moment, as I said, but I hope if you can't see it, just let me know. Okay. So this is the demo setup at the moment. At the front here, you can see the motor. It's turning a shaft, and here on the right-hand side, you can see this conveyor belt, which is in the end driven by this motor here. We have also installed, you can see it on top here, a cycling brake, which is not normal, but it fulfills a certain purpose, and I will show you this purpose in one of the slides afterwards. On here, we have installed a so-called on the bottom here, a so-called linear table, which is equipped with a 3D magnetic sensor. On the back side here of the demo, I hope you can see it. We have an end of shaft GMR angle sensor, current sensors, and MEMS microphones over here, plus the controller area, which is over there, which is equipped with some ARM Cortex M4 with Ethernet connection that we can get it to the cloud. A main controller for collecting the sensor data, as well as storing the motor logics, as well as a 3-phase BLDC driver. So I hope you could get an impression of this demo of Infineon, which is our so-called predictive maintenance condition monitoring demo. And I'm now showcasing you in some of the slides what the purpose of this demo and the brake that I hit right now is. So the demo is standing still. I'm switching back to the presentation mode. Just give me a few seconds here. I'm switching that off. Okay, Markus, just give me a hint if you can see the presentation.
Yes, perfect. Go ahead.
Big and clear. Okay, very good. So just a short intro into the topic of predictive maintenance and a short background. So we have a few requirements while collecting those sensor data in the field. You can see it on the right hand side. This is we need a certain level of efficiency. We need to monitor the life status of those data in the field. All this needs to be done remote or needs to be remotely controlled, and we need trusted devices and secured information flow. The target here, and you can see it on the bottom, is we want to avoid unpredicted downtimes. We want to prevent, especially in the industrial environment, from spontaneous event. We want to analyze and compare the data in order to use it and improve them. And in the end, we want to save resources, build up knowledges, and calculate a certain probability of occurrence, which helps us to predefine certain events or let's say not only events but certain actions that needs to be done if it comes to a maintenance case. This is the predictive maintenance demo as you see it on the front from the front. It was last year on our sensor and test exhibition booth, and this is the top view on our demo. As you can see, and I showed it to you in this video, you see on the right hand side, the white one is the conveyor belt which we are simulating. Then we see that linear table down there, the brake, the cycling brake, and the BLDC motors. Those are the functions, and I would say in the end also the interaction points of this demo. And then separated by the components that we use. I showed you on the top the control and actuate area. And then we have 4 major sensing areas that I'm going to present you right now. So let's start with the cloud dashboard. So we created a cloud dashboard. It's done via Amazon FreeRTOS. What you can see in this dashboard is on the left-hand side, the monitored current status. On the right upper side is the respective angle arrow. I will have a short intro on that one as well, some slides later. On the lower left-hand side, you can find information about the speed and the direction, and also some sound pattern analysis on the right-hand side. So we started a motor. I've shown that to you. Please apologize for that picture, but as I said, this session is a little bit more hands-on and pragmatic than we have done it before. So this is actually the BLDC motor that you can find on the lower left corner of the picture. And what we actually do if we talk about controlling a motor, I'm presenting you now those are the pictures directly taken from the demo itself. I'm presenting you the components that we use. So we used here for the major communication to the cloud, we use the XMC 4800 running on Amazon FreeRTOS. It's a 32-bit ARM Cortex M4, and we connected it via Ethernet to the internet, and it's securing all those data that are collected on the demo is transmitting those data securely to the cloud via our Infineon security controller Optiga Trust X, which is enabling a so-called DTLS communication part here to the internet. We have an XMC 1100 as a main controller. This is the second component that you can see. It's a 32-bit ARM Cortex M0. The CPU is running at 32 megahertz, and we programmed it here for demonstration purpose via the Arduino IDE. All the software here is available from our side via GitHub, and it's the main purpose of this CPU here is to collect, or this MCU is here to collect the sensor data and controlling the motor logic. The third part in this row is our three-phase BLDC motor driver shield. It's equipped with a so-called e-power device. It's the TLE9879. Which is a single chip three-phase motor driver. Also, this one is Arduino Uno compatible, and it handles more or less the motor commutation of this BLDC motor. It's already flashed with several motor control algorithms like sensorless FOC, back EMF, and the usual or common block commutation via Hall sensors. So this is in a nutshell the overview on the control and actuate part of this demonstrator. And now we've started the motor. You've seen that in the live demo that I've showed you. What happens in the dashboard is now that you can see that the current and the speed is increasing. So on the left-hand side, those two cuts of the dashboard show this to you. So on the lower left side, you see an increase in the speed. So we are measuring the speed of the conveyor belt with a specific sensor. I'm presenting the sensor to you afterwards, as well as you see an increase in the current. And the angle arrow is also starting to increase, as well as the sound frequency changes while starting the motor. So coming to this sound frequency change, I directly want to jump on the component that we used here. It's the IM69D130. It's premium, I would say premium microphone with an excellent signal to noise ratio of 69 dB. And is able to capture the audio signal completely distortion free with just one or less than 1% total harmonic distortion up to 128 dB. comes with a digital PDM interface and is usable for wide frequency responses from 28 Hertz to a 20 kilohertz. So this is the microphone that we use, and this also is reflected on a dashboard that you've seen right now with this sound patterns, these frequency patterns that you've seen on the dashboard. So coming to this cycling brake and the intention behind it. So I presented you, this is not an, I would say, a normal setup, but this brake has some purpose, as I mentioned at the introduction. We wanted to simulate a specific resistance here, especially a resistance at the shaft, which can happen in the field as well, a kind of shaft friction. The pressing this handle will cause the motor to brake, and in the end, the speed decreases shortly, but the motor, since the motor is controlled for constant speed, the speed increases and the current consumption increases as well. So we are causing here artificially causing here a resistance with this cycling brake at the motor in order to simulate certain resistances, shaft frictions in the demonstrator itself. So what happens in the dashboard is now that you can see on the left upper side a current increase, which is indicated via this arrow, this black arrow, and in the lower left corner you can see a speed decrease, as I mentioned it before. We have, in order to measure, I'm starting now with the current sensing. In order to measure the current of the motor running through the motor, we have this new industrial current sensor. It's the TLI 4971. It's a Hall-based magnetic current sensor, which is able to measure currents up to a full scale of up to 120 amps. And we want to, as I said at the beginning, we wanted to simulate a resistance in the system with this cycling brake, which leads then to a current increase of the motor. So a short introduction to the sensing principles of this current sensor. So we have those core-based solutions in the field that you might know from our competitors, which are more or less relying on a conductor plus a field concentrator and a field probe. In most of the cases, it's a Hall probe. So the field gets concentrated and picked up in this field concentrator, and the field probe is then converting this magnetic field into respective signal outputs. Our way at Infineon is a little bit different. We are following the so-called coreless open loop solutions, which is a solution that is not relying on a field concentrator, meaning the current is really flowing through the device, and the device itself is equipped with two Hall probes. You can see those Hall probes, the gray indicated areas in that picture are the two Hall probes. They are here picking up this field that is generated by the current flowing through the device, and this brings some advantage. So we have here an excellent stray field suppression through this differential measurement of these two Hall probes. We have no saturation, no hysteresis, and a higher linearity compared to those core-based solutions. And in the end, this leads to a low dependency on temperature and lifetime, and the sensor itself, so this TLI 4971, comes in a small SMD package. So if you look at the figures and facts of this TLI 4971, of this new industrial current sensor of Infineon, I would start with the left-hand side, which are the product characteristics. So the sensor is offering you a measurement range up to 120 amp AC and DC. Is offering a high accuracy over temperature and lifetime, means roughly about 2.7 to 3% accuracy here. We have an analog output stage with a high bandwidth of 120 kilohertz. And the nice thing is we are offering here two fast overcurrent channels with a signal delay of just 1 microsecond. So they are pretty fast. And this is exactly what we used here for when a user or a customer is coming to the booth and and hitting the brake, we are using those overcurrent channels here to stop and brake the whole system. Yeah, this is one of the main advantages of this device here. As you can see, the device itself is comes in a small SMD 8x8 millimeter package. On the right hand side, you can see the block diagram. Right upper side, you see the block diagram. You see the current rail highlighted in black. Then the two differential Hall probes highlighted in orange. The signal processing and the amplification, and then the analog output on the right hand side. As I said, the product itself, I think it comes in one of the slides afterwards, can be, so the overcurrent channels can be freely programmed by the customer, and also the measurement range can be programmed from 25 amp to 120 amp full scale range. Good. This is how the product looks like from a top view and from a bottom view. You see here so if we take off the package, you can see here the insides of the product. So we have here the high voltage side, which offers a functional isolation of up to 1150 volt. And the low voltage side with the pins and the insulation plate. And here we installed the clearance distance of 4 millimeters to guarantee this high voltage isolation, or this high functional voltage isolation of 1.1 kilovolt. The two Hall plates are placed in there, and this is also this picture here is also showing the current path. So as I said at the beginning, so the current is here really flowing through the device, and the magnetic field is here picked up at those two Hall plates, and due to we call this kind of hockey stick configuration, we have a low insertion resistance of just 220 micro ohms. Which in the end leads to very, very low power losses of the overall design and system. Good. Then this is a typical application, a motor control application. So the solution here is clear. So we want to have enable a smooth operation, smooth motor control. We said we can do this with a highly accurate measurement of less than 3% over temperature and lifetime. The protection of the output stages against overcurrent events. We did this with the two independent output pins, which can be freely programmed by the customers. We have an accurate in-phase measurement in harsh environments, so we are stray field robust through due to this differential measurement, and we are galvanically have a galvanic isolation installed between the current rail and the sensor, which leads to a functional isolation of up to 1.1 kilovolt. Those are the order information. All those parts you can get at Rutronik as well. So if you have the need of such a current sensor, so please ask Marcos and get in contact with your local Rutronik FAE or salesperson. So those are the information about the eval boards and kits. On the top you can see our high-end eval board and programmer, which means you have a 3-phase eval board plus the respective programmer. And on the bottom side you can see our so-called to-go kits and Shield to Go, which offer you testing of kind of basic, I would say, basic functions of this device. Yeah. Okay, and this is exactly the interaction point too. It's the so-called overcurrent protection. So we want to prevent the motor from severe damage via this current sensor. In that case, we implemented, if the current consumption is bigger than 7 amp, the OCD, so the overcurrent channel threshold is exceeded, the motor is shut down by the main controller. And this is exactly what I've done before when I hit the brake. What you could see in the video at the introduction. Good. The next thing, and this is also measured by and shown in this demo, is our double Hall sensor. It's the TLE4966G. It's used at the side of the conveyor belt. So we stripped a magnet at the side of this conveyor belt and placed this double Hall sensor below this conveyor belt to measure the rotational speed and direction of this conveyor belt. In general, we have a wide portfolio at Infineon of magnetic Hall switches and latches. They can be used mainly for proximity detection and rotational speed and direction measurements, as we do it with the TLE4966 in this demo. This is the product we are talking about. So it integrates two Hall sensor elements in just one package. And we have two pins available here. One pin is for speed and the other one is providing the directional information here for the main controller. We have excellent sensitivity and stability of the magnetic switching points here in this element, and also an operation operation from unregulated power supply is guaranteed with a reverse battery protection of -18 volt. The sensors are available for horizontal measuring and for vertical placements, which gives our customers the opportunity and freedom to mount it, I would say, flexibly on the respective application. It then looks like this. So you have, in the end, you have a magnet with multipole magnet, and you can see on the right hand side the sensor with the two Hall plates or Hall probes integrated, and once the direction and the speed changes, the two Hall plates will pick up the magnetic field and provide this via the two pins to the main controller. The customers of us are mainly using it in the automotive environment for windows and a sunroof. In the industrial and consumer environment, they get used mainly for power closing systems like garage doors, sun blinds, shutters, and other automated doors. Okay, then we come to this so-called linear table, which is mounted in the end between the shaft of the motor and the beginning of the conveyor belt. So the shaft is turning the conveyor belt, and we mounted this linear table below this shaft. Even here, this I would say this linear table fulfills a certain purpose. In the end, we want to simulate anomalies in two differing modes of angle calculation. So we have one sensor implemented on the backside of the motor as a so-called end of shaft configuration. And with this linear table and a 3D magnetic sensor here, we are more or less fulfilling the needs of out-of-shaft configuration here. So we strip the magnet over the shaft, and this 3D magnetic sensor is able to measure magnetic movements in X, Y, and Z axis, and this is what we want to showcase here. The purpose is, we say, we can, by comparing the highly precise measurements of this GMR angle sensor, which is in the end of shaft configuration, compared to this 3D magnetic sensor, which is in the out of shaft configuration, we can simulate shaft failures, for example, the wobbling of the shaft. This is how it's set up from a top view. So you see on the left-hand side the end of shaft configuration with this high precision GMR sensor, and this linear table. This is this out of shaft configuration of this 3D magnetic sensor. So just a few words to this, starting with this end of shaft configuration with the TLE5014 SP. It's our digital GMR angle sensor, which is coming with an SPI interface, and it detects the rotation of fast spinning motor shafts, and can be also used for highly precise motor commutation, for example in FOC or sinusoidal commutation. So this is our, in general, just an overview for you. This is our portfolio of angle sensors. So we have AMR, just from a technology point of view, we have AMR, GMR, and TMR sensors. You can see that on the upper side of this PowerPoint slide. On the left-hand side, you can see the output signal that the respective sensor is providing you. And in that case, we have the TLE chosen this TLE 5014 SP. The D behind this, the numbers and the product name indicates a dual die version. So we have also dual die components for high safety applications in industrial and automotive applications. So let's have a short look at this TLE 5014. As I said, it's a GMR digital angle sensor. It's providing a 12-bit digital interface, usually with the protocol options PWM, SEND, and SPC. They are available as single and dual die products, and it integrates E2 PROM and a lookup table to store customer configurations and customer values or customer application values. It provides you a high angle accuracy of maximum or angle error of just 1 degree over temperature and lifetime, so means over whole temperature and whole lifetime of this device. The device itself is completely developed according to ISO 26262, which is an automotive standard, here it's developed according ASIL-D level, and the sensor itself is reaching ASIL-C metrics. On the right lower corner, you can see the device that I will talk about and present you today. It's a TLE 5014 SP, so the one with an SPI interface, as I said, for high dynamic applications. It's an, as I said, fully compliant sensor developed according to ASIL-D. It provides you 3-pin SPI with access to the sine and cosine row values and calculated angle of 15 bits and an SPI data rate of 8 megahertz. The sensor itself provides an internal update rate of 25 microseconds, and is available as a 3.3 and 5 volt version. The accuracy that we claim here is definitely less than 1%, 1 degree out of the box. Just a short look at GMR angle sensors and the magnetic field performance of GMR angle sensors in general. So if you do a one-time compensation, you can get the angle error of the device itself down to, I would say, less than 0.5 degree. If you use a fully compensation, or you fully compensate it over temperature, you can get it down to 0.3, 0.2 degree angle, 0.6 degree angle error over temperature and lifetime. So this is what we claim for our GMR sensors here. So it's quite interesting, I think, for you to see what you can do with the sensor and how you can improve it while storing your application-specific and customer data in the lookup table of the sensor. So then coming to this out-of-shaft configuration in this linear table, I mentioned it before. So we are using here our TLE49 3D W2B6, which is a 3D magnetic sensor with integrated wake-up functionality. As I said, we are using it here in an out-of-shaft configuration, and using it here together while calculating the angle error for predictive maintenance compared to this end-of-shaft configuration of the TLE 5014 that I presented you before. And the difference between this end-of-shaft and out-of-shaft angle calculation can be used for predictive maintenance purposes, meaning as soon as you increase or the angle error increases, there must be some wobbling or some resistance or some issues with the gear and the shaft, or misalignments of the shaft of these motors. This is what we want to simulate here. So an unbalanced shaft, and therefore, and I can tell this to you right now, this this linear table can be moved by the customers, so you can increase by moving this linear table by pushing it forward or backward. We can increase the angle error which between the TLE 5014 and the 3D magnetic sensor, and therefore we can simulate those wobblings or issues with the motor gears. Let's start with a short overview on the 3D magnetic sensors. They can usually be used for linear position detection, angular position detection, as we do it right here, or 3D movements, for example, like joysticks or rotation knobs. And this is our portfolio of, a little bit confusing at the first glance, but the product that we are focusing on is this on the right-hand side, highlighted in this purple rectangle. So it's a TLE 49 3D W2B6. A0 to A3. I will afterwards give you a short introduction on what this A0 and A3 means in terms of the features of this device. So the unique characteristics you can see on this slide. So the sensor itself is available in 3 different variants or derivatives. As I said, A0 to A3. It comes with an I2C interface. So those 4 versions have already a specific addressing. So an individual startup ID that is pre-configured by Infineon, and this allows you to connect it to one I2C bus. So at least the 4 derivatives to one I2C bus. The microcontroller is directly knowing which sensor and which derivative he's talking to. This is one nice feature of those TLE 49 3D W2B6 with those 4 derivatives. And another nice feature of this device is the so-called wake-up functionality. In case that low power consumption is key, you can see it on the left hand, on the upper side, you can see the magnetic field on the X, Y, or Z axis, and on the lower side of this picture, you can see the interrupt functionality. Means as soon as the magnetic threshold of this device is shifting or changing, or in the end, let's say if the magnetic threshold here is exceeded of the device, the 3D sensor is sending an interrupt to the microcontroller and is waking up the overall system. In low power mode, the sensor itself has an current consumption of just 7 nanoamp. However, I would say in normal mode is definitely more. I don't have the figures with me now, but it's definitely more. But the low power mode of the device itself is just 7 nanoamp, which is caused in the end also by this nice wake up functionality of the device, waking up the microcontroller and the overall system. Now, what we are simulating here, and then coming to the third interaction point. So we are simulating here a wobbling or an issue with the motor gear. So my colleague in this video was shifting the linear table from left to right, and as you can see on the right upper side, the angle error is significantly increasing, which is then an indication for us that there must be something wrong in the system. We can shut down the system and prevent it from damage. The whole demonstrator was built up with our evaluation tool environment for those devices and components that I've presented to you right now, which are our to-go kits and the so-called Shield to-go. The to-go kits you might already know. The to-go kits always combine an ARM Cortex-M0 plus the respective sensor and a USB connection and the onboard debugging. Whereas the Shield to-go just comprise one single Infineon IC, in that case the sensor. They come with solderless connectors, and the software is available, or I would say in general, low-level drivers are always available, but in this case, also the Arduino software or the software for the Arduino IDE is available on our GitHub account for fast evaluation and fast testing. So we are providing here two types of software. One time is the graphical first type is the graphical user interface, a GUI, a dedicated GUI, and secondly, some low-level drivers plus the Arduino libraries. And all those sensors, especially the magnetic sensors, come with those so-called, we call this add-on components, means you can see on both the to-go kits and Shield to go's this hole, which is part of the PCB. And this allows you to mount these add-on components, which are equipped with the right magnet, on top of these devices and directly test it. So you don't need to care about any magnetic magnets or magnetic designs. You just take and select the add-on component you want to use in your application. So example for rotational movements, you can take the rotation knob, which is down there, and just mount it on a 3D magnetic sensor and start evaluating without caring about the respective magnetic design. So this is one big advantage that we have here for our devices. The setup is quite easy for this Shield to go. So we have, I would say, standardized form factor, standardized PCB and layout. The only thing that changes is the IC on top of it, and those ones you can combine via those adapters to so-called systems and use it, for example, on an Arduino Uno, or here in this example with our XMC 1100, which also comes in the Arduino Uno form factor. The libraries, as I said, are also available and are open source. This is the portfolio of Shield to go, so quite a wide range. I think we enlarged it in the last weeks by another few sensors. So we have, starting from the top to the bottom, we have available our barometric pressure sensors, the MEMS microphone that I presented to you, our current sensor, the 3D sensor, as well as our double Hall sensors, and also simple Hall switches are coming in this form factor. Then we have the microcontroller, the XMC, which has the same pin layout, I would say. The adapter for the Arduino Uno, we will launch this year also an adapter for the Raspberry Pi, which then comes in the pinout for the Raspberry Pi. And also the security ICs that I mentioned at the beginning, so the Trust E and the Trust X, are also provided in this standardized pin layout PCB form factor. So how is that looking like in the end? I'm just giving you an impression. So this is a 3D magnetic sensor mounted together with this rotation knob on an XMC to go. And this is, for example, then different Shield to go, mounted on one of those Arduino or this My IoT adapters, which come in the Arduino Uno form factor, mounted on an XMC 1100 bootkit. So you are able to test different sensors and ICs of Infineon with just more or less one device then. Another hint from my side is our online simulation tool for our magnetic sensors. So here you will be able to simulate before you purchase them, before you build them in your application and you want to try them out. You have the ability here to test and simulate it online. So you have the option to choose between the different derivatives of the 3D magnetic sensors, the Hall switches and the angle sensors, and you can really here customize your application in terms of you first select the sensor, you then select the magnet, you can select application specifics like the tilt, air gap, magnet type, and so on and so forth, and you can simulate it here and you get an excellent analysis and result in a PDF format of your magnetic circuit. So try that out. This is available online from our side on our webpage. As I said, for the 3D magnetic sensors, the Hall switches and the angle sensors. Yeah, last but not least, this is the last slide and then I'm done. Our overview on sensors at Infineon. So we have the magnetic position sensors with the 3D magnetic, the angle sensors, the Hall switches, and the linear Hall sensors. The rotational speed, mainly for automotive with wheel speed, engine, and transmission. Our pressure sensors, also mainly automotive based for side airbag, barometric manifold, TPMS for tire pressure management, measurement systems, and the silicon microphones. And in the end, which is not open market, but I mention it because also part of our white portfolio is our ADAS and wireless portfolio. And the new member, our magnetic current sensors. Good. That's it from my side. This was 40 minutes. I'm done, which is good.
So
handing over back to Markus. Thank you for your time.
yeah, thank you, Tobias, for the nice presentation. What I learned today, I even know it before, but I recognized again that Infineon is much more than just selling power products. They are strong in that, but for sure, what I said already initially. Meanwhile, they have a competitive and, from at least from my perspective, industry-leading portfolio on sensors, where you as a customer definitely should know about. So what we will do now is to wait for your questions. So please use the Q&A function, what I initially said. So press the 3 dots in the menu line, and then you have the possibility to ask questions. So preferably send it to host and presenter, that as well Tobias as well as I can see those questions. And then we are fine to reply to that question. If there are no questions coming in, we will also open the microphones for a short time. Just that if you prefer to ask your questions verbally, we can also do that for sure. So yeah, we give you some seconds to raise your questions. In the meantime, again, what you have seen today is that Infineon has really the capability to reduce your time to market significantly due to all the nice eval boards, eval kits they offer. You really have the chance to accelerate your application quite fast. And the good news for you is everything is available through Rutronik. So just contact me or contact your local sales contact, customer service, whatsoever, to get these eval boards and to start your predictive maintenance solution as soon as possible. Yeah, predictive maintenance is a big buzzword actually in the market, and there's a lot of things going on. We have a good know-how internally at Rutronik, so that we are happy to receive your questions, and hopefully then we can reply those questions through our sales and FAEs to help your designs.
Markus, so first question coming in. So the first one I think is more private one for you, but the second one is from Peter Schmidt. Where could I find the code at GitHub? So we have an own page. So Infineon has an own repository at GitHub. Just go to github.com and search for Infineon. You will find all repositories of the Shield to Go that I've presented to you, and of all the devices, the low-level drivers, the low-level C drivers of the devices that I presented to you, especially for the sensors, because I'm responsible for the sensors. They are available on our website. So you can find it on our website on the respective product pages. I hope this answer helps you, Peter.
So another question, can you provide URL for this presentation? So what we will do is so we record that one, and we will upload that either on our website, or probably we also will send the link to all the participants of today. So we definitely will inform you, the ones who joined today, where you can find either the presentation or even the recording, so that you can check again if there is some open points afterwards. Any further questions from customer side? I don't know, Tobias, if you see some more.
No, not yet. But if there are one, at least they know our names, so they can either call us, give us a hint, or write us, whatever they want.
Yeah, probably I will open now all the microphones, so that you can also ask your question verbally if you preferred it. So now everybody.
No.
Further question you want to ask? Okay, there is another question from experience with a business. So I will mute. So, Tobias, could you reply to that questions? Any experience with sensors in railway business?
In railway business, yes. I actually had one. I can't tell you the region because of compliance purposes, but we definitely have customers that are using our magnetic speed sensors for railways. Yeah. So if there are dedicated questions, I would ask these persons to get in contact with you so that we can talk about it. So I know from that business that those customers are asking for. I would say high quality standards, and also for yeah, a guarantee that the products themselves will be produced for the next 10 to 15 years. So as a good, I would say, good opportunity to discuss here. Yeah.
Okay.
Yeah.
So I will use that. I know that the person who raised this question, I was in contact before, so that's good to have this conversation again.
Yeah.
So anything else? I can see another question regarding the security controller on the XMC 4800 board. Can you please tell us more about how it works? Does it provide hardware encryption? Also, the way communication is secured to the cloud.
Yeah, this is a topic I'm not an expert in, so I would take this question with me and address it to the respective experts from the product line. I know that this is based on hardware encryption, so this is a security, high-end security controller. But for the purposes that for more details, I really kindly ask you, please provide your contact information to Marcus, and Marcus can then get in contact with the respective experts from the product line. Yeah,
I already took out the question
yeah.
to the overview of the participants. So so the one who raised this question will get a reply through Rutronik.
Yes, please. Yeah.
There is another question. Can you advise some wireless devices protocols for IoT from Infineon?
Yeah, as you know, we have successfully acquired Cypress some weeks ago, but Infineon itself didn't offer any wireless protocols or standards like BLE or, for example, Wi-Fi. So in that case, I kindly need to remind you that you might need to wait for the let's say final days of the Cypress acquisition. Yeah, then we can have a discussion here with the new portfolio. Yeah.
Okay. I don't see any further question. Maybe Tobias, you received another one.
Nope, I didn't receive any more, but just the one on the software from Peter Schmidt regarding the code on GitHub. But this is already answered. So from my side, that's it. I just wanted to thank you for your time and also your patience regarding the demo and the overall setup. I hope you enjoyed it. A little bit different than normal, but also a nice experience from my side. Yeah. Thank you, Rutronik, for the time.
Yeah. Okay. Then also thank you from my side. First of all, for sure, for the customers that joined today. I hope it was a lesson where you learned a lot about the competitiveness of Infineon. And I would love to stay in contact with you if you raise further questions afterwards, or if we can exchange about your predictive maintenance applications you're currently designing. Feel free to contact me. And also thanks to Tobias for presenting today. I think it was a good overview to get another view about Infineon. and the competitiveness they have in the predictive maintenance. So thanks again. Enjoy the nice weather. At least we have it here in Germany. So we're expected to have 30 degrees by end of the week. So we should enjoy that. Stay safe, stay healthy, and thanks for participating. Bye bye.
Thank you. Bye.